Curious Droid.
Hello and welcome to another Curious Droid Live with me, Paul Shillito. And in this episode, we're going to be looking at the future. The far, far future. In fact, to the end of the universe and what we think might happen. We can only postulate because obviously we've only got our theories of what may happen in the far distant future based on what we've actually built up from looking at the time up till now and the various things that we know and we think might happen. But to help me sort of explain what we think might happen and what possibly could go on there, we have Ethan Siegel, who is... Here we are. Hello, Ethan.
Hi there, Paul. Hi there, all you Curious Droid listeners.
Yeah, Ethan is a theoretical astrophysicist and science writer, and also has a regular blog with Forbes. And now, let's see. What we're talking about here is something which is, I find, rather sort of mind-boggling in some respects, because it's so far off when we're sort of looking at the future. I mean, we normally think of day to day, year by year, maybe obviously to a few million years ahead where we might think what might happen. I mean, even then, the human race as we see it will be completely different. But going beyond this, we're going beyond our species. We're going beyond the existence of our sun, our solar system, even our galaxy. It's going way, 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 way beyond that, right to the very end. And we're going to be talking some pretty, excuse the pun, astronomical numbers, and that's in time, in years. So I think the best thing to do is if we could sort of start off and say, we know we've come from the Big Bang, or this is our best theory so far. How does what we know now sort of guide us to where we think we're going to be going in the foreseeable future as far as the long term goes?
You know, that's a wonderful question, and I'm so glad you asked it, Paul. When people think about, like, well, we know where we came from, but how do we know where we're going? That's one of the most powerful things that physics in general has to offer. It says, hey, if you know the rules that govern the universe, you know what's in the universe because you measured it, and you learned what were the initial conditions that you started the universe off with. So if you know those three things, what the laws are, what makes it up, and what it started off as, then you can figure out, you can calculate, how did it get to be this way? How did all the things, take place, transpire to give us our universe today? And then since we still know the laws of physics, we can extrapolate how it's going to behave into the future. So when you say, well, we know about the Big Bang, yes, we do. But it's not like, oh, we made a theory and it sounds good and we went with it. It was like, no, we had things that we went out and we observed that led us to formulate this hypothesis of the Big Bang. In particular, what we noticed was when we were looking at all the different galaxies in the universe, the close ones and the super far away ones, what we were finding is the farther away a galaxy is, the faster it appears to recede from us, and the more red-shifted its light gets. And the reason for that, we think, is because in relativity, we have light traveling through space, and light is defined by its wavelength. The size of your wavelength tells you how much energy your light has. If space itself is stretching, then the wavelength of light should be stretching, which means the universe should be cooler today than it was in the past. And that also means when the universe was smaller and the wavelengths were shorter, the universe was hotter. So we expect, if we go back far enough, that there'll be a time when things were so hot that we couldn't have neutral atoms. And we actually see the leftover glow from that. That was discovered in the 1960s. That's why and when we accepted the Big Bang as our leading theory of the universe. So anyway, you go all the way back and you say, okay, the universe is full of stuff, And how has it expanded? So you measure what's it like 1 million light years away, and 1 billion light years away, and 10 billion light years away, and you see how the universe has changed over time, and that tells you what's in it. So that's why we know we've got about 5% normal matter, stuff like you and me, things made of atoms, protons, neutrons, and electrons. But we also have a universe that's about 27% dark matter, which is some new type of matter that isn't made of the things that make up atoms, that doesn't interact with light, that doesn't smash into each other or things like us. And we also have 68% dark energy, which is energy inherent to the fabric of the universe itself. And then we've got a tiny little bit, less than 1% of like neutrinos and radiation and all of that. So you say, okay, that's what makes up my universe. I know the laws that govern it, right? It's general relativity. And you say, okay, I know how it started and what it looks like today. That's how you derive how it's going to behave in the future.
Right. So now this is another thing which it confused me at first when I first heard about it, was that the universe is about 13.5 so billion years old. Yet, because it's been expanding at the moment, it's now 46 billion light years across. So it's how fast is the actual universe expanding in sort of speed that you could sort of relate to sort of light years or something like that?
Okay, that's a really good question. So, if you, a lot of people think, for example, if the universe is 13.8 billion years old, then I should be able to see 13.8 billion light years in any direction I look. And that
Yeah,
would be
yeah.
true if the universe weren't expanding, right? If I had something over here, 13.8 billion light years away, and it emits some light, that light's going to travel to me, and 13.8 billion years later, the light arrives. But if the universe is expanding, then if something starts out close to me and emits that light, the light's going to move towards me, but the space between me and this light is going to expand. So as the light comes towards me, the space between us is expanding. And by time the light arrives, sure, it might have traveled a total distance of 13.8 billion light years. It might have taken 13.8 billion years. But the thing that emitted that light, because of the expansion of space, it's now much farther away. Like you said, 46 billion light years. So that's how the expanding universe works, to mean that things are actually larger than the amount of time it took light to travel that distance. Um, so then you say, okay, well, I really, maybe I can grasp that part, but how confident are we that this is right? How confident are we that this is correct? And the answer is we have to look at a bunch of different lines of evidence. We want to look at different distance indicators. So we'll look at individual stars, and we'll look at properties of galaxies, and we'll look at ultra distant supernova explosions, and we'll put that all together to map out how has the universe expanded over its history. We'll also look at that leftover glow from the Big Bang, when atoms first became neutral and this radiation stopped bouncing off of all the electrons that were out there, because now the electrons are bound up into neutral atoms, and all of a sudden this light comes towards us. It gets stretched and shifted. Light that can ionize an atom has to be ultraviolet light, but over the expansion history of the universe, that light has redshifted through the visible portion, through the infrared, all the way into the microwave. And that's what we see. If you've ever heard of the cosmic microwave
Yeah.
background, that's our term for the leftover glow from the Big Bang. The fact that we've seen it and measured it, and that it has the exact properties that the Big Bang predicts, that is really, really strong evidence that the universe did in fact start with a bang.
Right. So, but so we've got the universe expanding out at the moment, and this is driven by what we think is dark energy. That's our best explanation at the moment. So, if it's going to keep expanding and expanding, What are the implications of that as we go further and further through time?
Oh, that's a great question. So you had said, hey, in terms that we can relate to, how fast is the universe actually expanding? And when we think of a rate, we normally think of a speed, right? Things happen like at this many kilometers per second. Well, the thing is, with the expanding universe, we can give you that rate, but it depends on how far away a galaxy is from you. So a unit we use a lot in astrophysics is a megaparsec. A megaparsec is about 3.26 million light years. And that's just a definition. You'll just have to accept megaparsec is a pretty big distance that talks about the separation of galaxies. Well, for every megaparsec away a galaxy is from another galaxy like ours, it will expand away at about 70 kilometers per second. So if something is 10 megaparsecs away from us, it'll appear to recede at 700 kilometers per second. If something is 1,000 megaparsecs away from us, it'll appear to recede at 70,000 kilometers per second. And if something is about 4 or 5,000 megaparsecs away from us, it will actually appear to recede from us at the speed of light or faster. So what this means for dark energy is that this expansion rate, you can imagine the universe could go in one of three possible ways. Okay, you had the Big Bang, this initial expansion, and everything's receding from each other. But you also have gravity, which is working to pull everything back together. And you can imagine, just like your old Goldilocks and the Three Bears story, you've got the three possible outcomes. Either you've got this universe is too fast, and everything expands away, and gravitation tries to pull it back together but can't. Or you can imagine this universe is too dense, where everything expands and the universe pulls it back together and it recollapses and ends in a big crunch. Or you can imagine the just right case, where it's right on the edge between recollapsing or expanding forever, so the expansion asymptotes to zero but never quite gets there. For those of you who don't know what an asymptote is, it's like your student loans. You think you're going to pay them off, and you pay and you pay and you pay and you
Never
pay, but
ends.
you never quite get there. That balance never reaches zero.
Right. So, our best guess scenario at the moment, because I think we've got the one where it collapses back in on itself, and we've got almost like then a cyclical universe where Big Bang expands and then gravity eventually takes over and it falls back in on itself. We've then got, well, I think you called it the Big Rip, where it then expands out. But it doesn't the Big Rip, which expands faster, then fall back in on itself again?
Well, no, that's not what the Big Rip does. So if you
My
wanted to
mistake
call it
then.
the Big Rip, that's a special case of this expands forever scenario. That would be a case where you had something driving the expansion that it actually sped up faster and faster and faster.
Ah,
So instead of this rate I told you of 70 kilometers per second per megaparsec, that would go up over time, and it would become like 100 and then 200 and then 1,000 and so on, and it would literally tear everything apart. The type of universe we live in, to the best that we've measured it, is going to have an expansion rate that asymptotes to not zero, but some finite positive value. So let's say 55 kilometers a second per megaparsec. Well, that means if a galaxy is 1 megaparsec away to start, it'll expand away from us at 55 kilometers a second. But then by time it's 2 megaparsecs away, it'll expand away at twice that, at 110 kilometers per second. And as time goes on and this galaxy gets farther and farther and farther away, the expansion rate is going to tell us it's going to appear to be pushed away faster and faster. That's what dark energy does. That's our fate of the universe. And that's why we say the expansion is accelerating. It's not because that expansion rate is going up, it's because the speed of any individual galaxy as we see it moves away faster and faster and faster. So that's what we expect to happen on really large scales. In our local group, we have beaten the expansion of the universe. The Milky Way is bound to Andromeda and all the other small galaxies in the local group. Eventually, over time, we will all merge together into one enormous elliptical galaxy. We call it Milkdromeda. It's a galaxy that doesn't yet exist, but we've already named it. Everything else that's farther away in the universe, we're going to see it continue to recede at faster and faster and faster rates. Over enough time, these galaxies will reach such a great distance that they will become unreachable. Which means even if we left Earth today at the speed of light, we could never ever get there. In fact, and this is going to be a disappointment to some of your listeners. If we were to look at all the galaxies within our observable universe today, only 3% of them are still within reach. 97% of all the galaxies in the universe are already out of reach, where even if we left today at the speed of light, we'd never get there owing to the expansion of the universe.
So already we've actually lost that. But we've been going 13.8 billion years. Now, our star, our sun, is going to work for another 5 billion years before going to red giant and then throwing off its outer shell. And then effectively we will become a dead solar system. But obviously there's going to be a lot going on from there. What's the sort of the next stage on from when our star dies, and how far further forward in time can we expect things to keep generating stars from a material that's thrown off and it goes on the next one and the next one and the next generation and so on and so forth?
That's a really interesting question. You know, when you talk about the stars in the universe, what most people don't realize, we sort of get taught that our sun is just a typical star, and that's not true. Our sun is more massive than about 95% of the stars in the universe. The overwhelming majority of stars are these small, low-mass red dwarf stars that are smaller and fainter and cooler than our sun is. These red dwarf stars, they actually live a very long time. This is a little paradoxical. You would expect that a bigger star with more fuel would live longer than a smaller star with less fuel. But because these small stars are cooler, that means they burn through their fuel slower. They're at lower temperatures, so nuclear fusion takes a much longer time. So you get a slower, steadier output of energy. A star like our sun might live for, 10 to 12 billion years total. But a star like Proxima Centauri, which is a red dwarf, it's the closest star to us, but it's a red dwarf star, that might live 1,000 times as long. So as we're talking billions of years for a star like our sun, Proxima Centauri is talking trillions of years for its lifetime. Now then, if you're asking, well, can't we form new stars? Absolutely, we can still form new stars as time goes on because we have gas clouds in our galaxy. When stars die, they send their outer layers back into the universe where they can participate in future generations of stars and planets, etc., forming. So we should have new stars forming for hundreds of trillions of years. And the stars we do form, the ones that live the longest, might themselves live for tens to hundreds of trillions of years. So it's probably going to be quadrillions of years, or 10 to the 15 years or so before we actually run out of new stars that live and burn in the universe.
Yeah, so that means that we're going to run out of the very lightest elements to create nuclear fusion, and the hydrogen and then the helium. So what happens when all the stars have run out of those materials? Because obviously they can't form from the gas clouds because there's no more raw material left. All we've got left is dead stars and planets and rocks and bits of dust floating around. So how can things sort of still continue to a certain point there? Plus, also, we've got gravity, which is still trying to pull things apart, what you were saying on the local sort of cluster and in our and what is it? The Milky Andromeda. What was he called it again? The Andromeda Milky Way.
Milkdromeda.
Milkdromeda. That's it.
Milkdromeda.
Milkdromeda. Yes. So we've got that being pulled away. Yet the expansion is now going so far that gas can't sort of fall back in on itself because it's becoming too sparse.
Well, this is an interesting thing. The galaxy itself should stay the same size because once you beat the expansion of the universe, you've won. So we're a gravitationally bound big galaxy, Milkdromeda, this big giant elliptical galaxy. What's going to happen over time is these little swarms of stars and gas, they're going to gravitationally interact with each other. When you have many, many stars or masses in your system, what's going to happen is when they interact, two of them will become more tightly bound and a third one can get kicked out. So we have a fun word for this in astrophysics. We call this violent relaxation, which is a nice astrophysical oxymoron. So what happens is some of these masses will get kicked out, but other masses will get more closely bound together. Now, you're like, okay, well, you're going to run out of stars, you're going to run out of gas. Can you still make new pieces of, stellar life? And the answer is yes. Throughout the galaxy, including right in our own cosmic backyard, we have failed stars known as brown dwarfs. These are, collections of gas that do give off their own light, but don't fuse hydrogen into helium. So they have hydrogen in them, it just can't burn. Oftentimes, they exist in binary systems where you have two brown dwarfs that orbit each other. Or you can have independent brown dwarfs that through this violent relaxation process will become bound to one another. Eventually, they will spiral into each other and merge. And if they go above a certain mass fold, then all of a sudden these stars can come to life. They can build new stars out of two or more failed stars. And in fact, there's a pair of brown dwarfs about 10 light years away from us right now that we estimate in a long time in the future, quadrillions of years or even more, they will eventually merge together and become a red dwarf star. So even after the last star has died, we still have ways to form new stars and create new life. It's a wonderful thing to imagine that in our sci-fi future, after the last star has burned out, we could maybe find one of these binary brown dwarf pairs and shoot a spaceship over to it and just go into stasis mode. And when those two brown dwarfs finally merge together, then you get a let there be light moment, and your ship can turn back on with the new source of energy.
Which actually brings me on to another thing, because what we're talking about here is these unimaginable lengths of time. I mean, I was reading your article on this, and we're talking like 10 to the power of like 50 years. It's quadrillions of years. Is life as we know it still going to be viable at those far, far distant times? Or is the universe itself not going to be really sort of life friendly?
Well, this is I would love to tell you we know that because we have the same laws and the same ingredients and the same molecules, that no matter how far we go into the future, life's still going to have a chance. The fact is, though, we've only ever discovered one instance of life in the universe, and that is life on planet Earth. So I can't tell you, oh, how would it do around a red dwarf star if these red dwarf stars have a bunch of, solar flares? Would that wipe out the life on a world around one of those stars? Maybe. Could life sustain there even though the stars are cooler with less ultraviolet light? Would life still be able to happen with the same processes that happens here? I don't know. But I like to think that, and this is just speculation on my part, but I like to think that given the fact that we have life in the deep ocean where there is no sunlight around hydrothermal vents, given that we know the laws of physics and the laws of chemistry where you look at how atomic spectra and lines work, that they're the same everywhere we look at in the universe, that they're the same at all times, whether we're looking shortly after the Big Bang or today at the present day, whether we're looking billions of light years away or right in our own backyard. These laws are the same. I like to think the laws will be the same arbitrarily far into the future, so that if you get the right conditions where you have an influx of energy and you have the right chemical ingredients, carbon, oxygen, nitrogen, hydrogen, etc., that you will have another chance at life. So I like to think that this will continue, that as long as you have stars and as long as you have energy and as long as you have the raw elements for life, you have a chance for life to still exist, even 10 to the 15, 10 to the 20 years into the future.
Right. So going beyond that, and we get to a point where we haven't got any stars left, and the brown dwarfs have merged, become new stars, and effectively burned themselves out. And we get to what we call the heat death of the universe, where the energy of everything becomes so small that effectively nothing can happen. What happens to matter at that point? Because one of the things you say is that black holes will evaporate away through Hawking radiation. So if a black hole can sort of disappear back out and radiate itself out, providing we don't know that it might actually go somewhere else. We haven't worked that one out yet. But what happens to the actual physical matter, the planets, the rocks, the dust and things that are left over, which are now at such a low energy? Does that just bleed away into just energy or nothing?
Okay, so big existential question here. Does everything die, and if so, how? So, for a lot of it, yes. So, we have these bound galaxies or groups or clusters of galaxies that all accelerate away from each other. And that's going to happen. That's already happening. Aside from our local group, everything we know of in the universe is already unbound from us. And in just a few tens of billions of years, so in only a few times the age of the universe, Milkdromeda will be the only thing we can see in the night sky for hundreds of trillions of light years. So that's already on its way. Then you say, okay, we have all the stars and the masses, and they'll burn, they'll turn black because they run out of fuel. Some of them will form black holes. Then what happens? Well, violent relaxation is going to happen, so you'll get a few collisions and mergers between stars or stellar corpses. But for the most part, over enough time, you're going to have, oh, now this star or this solar system gets ejected and flung into intergalactic space, so it's all on its own. And in the meantime, in the center of the galaxy, we have a supermassive black hole that will continue to grow and attract and accrete and grow and create more and more matter inside. So in the end, you're going to be left with a few bound systems orbiting far away from the center of the galaxy, a black hole at the center of the galaxy, and these dead solar systems floating through intergalactic space. Over time, like you said, these black holes will eventually decay. This is known as Hawking radiation, where what happens is this black body radiation is emitted because space-time is so curved near the event horizon of the black hole. This curved space-time means that the quantum vacuum is different. And what Hawking derived, what his most famous work was in the early 1970s, was to say, yeah, this means that you get this black body, low energy spectrum of radiation, And where does the energy for that come from? Because from E equals mc squared, it's got to come from somewhere. If you have energy, where's it coming from? The answer is the mass of the black hole. So even though it might take 10 to the 70, 10 to the 80, 10 to the 100 years, every black hole in the universe will eventually decay away also into radiation, so that's what you're left with. So other than this sea of thermal radiation, what happens to these leftover dead stars, dead planets? Do they just exist forever? Well, through gravitational radiation, planets will eventually orbit into and crash into their stars. So you will be left with just these big clumps of matter in the universe. Will they decay? This depends on whether the proton as a particle is fundamentally stable or not. The neutron isn't. We know if you take a free neutron and you leave it in space, after about 15 minutes, it'll decay away. What about the proton? Well, we know if you take a free proton and you leave it in space for about 10 to the 35 years, it's stable. And the way we know that is because we gathered up, 10 to the 25 protons or 10 to the 35 protons, and we wait a year and none of them decay. And so we say, okay, the lifetime of the proton is at least 10 to the 35 years. Now, our universe is only 10 to the 10 years old. So it's possible that further down the road, we will find that the proton itself is unstable and decays away. And if that's the case, then yes, matter is unstable inherently, and it all will eventually decay away into whatever the proton decays into. But if it isn't, if the proton is truly stable, then what that means is all of these structures, these big collapsed masses, these stellar remnants, these rogue planets, whatever it is that's out there in space, it continues to exist out there by its lonesome in intergalactic space for all eternity.
So effectively, it would be for eternity, and that would be it. You just have a rock drifting through empty space with nothing around it forever, and that's pretty much it. That's a bit of a sad sort of end to the universe, really. I'd rather have it crash back into itself and then start all over again. But I suppose
it could happen, right? If dark energy isn't what we think it is, if dark energy, for example, reverses itself at some point later in time, then we could still have that. It's really important to remember that what I've told you is based on an assumption that the universe that we conclude we live in today is a good assumption for how the universe will behave arbitrarily far into the future. And even though we have good reason to believe this is the case, there's always more to learn. And any evidence that comes up in the future, as we make better observations, as we see things we've never seen before, as we make new discoveries, they could change these conclusions.
Right. Okay, well, I think we can come on to our questions now. And the first one from John Magnus Carlson. If Earth somehow managed to avoid being engulfed by the sun in the far future, obviously when it goes to sort of red giant, how long will the Earth exist? And I think we've almost answered that in the last question, but obviously we could run through that again.
Well, let's go for it. Let's go for it for optimistic points of view, right? So let's say the sun 5 to 7 billion years from now expands and becomes a red giant. We know it's going to engulf Mercury. We know it's going to engulf Venus, but it may not engulf Earth. There's a good chance that it can push Earth's orbit out to a greater distance, that when the sun expands, it won't quite reach where the Earth will be. And if that happens, then the Earth will get to keep orbiting around the sun. Over time, a day on the Earth will lengthen until, as the moon spirals away, eventually the Earth will become tidally locked to the moon and the sun. So we always face the same side of the moon, and it takes 47 days for the Earth to rotate on its axis. Okay, obviously we'll call that a day. So 47 times as long as the 24 hours it takes today. So then the Earth goes around the sun. Let's assume that the sun doesn't get smacked into anything, that the Earth doesn't get ejected. Let's instead say the solar system, the whole solar system, is one of those nice things that gets sent into intergalactic space and it stays there for arbitrarily far into the future. The only thing that will take Earth down is this slow gravitational radiation. As the Earth orbits the sun, it will slowly radiate gravitational energy away, which means it will spiral in very slowly. Just like the black holes that LIGO detected did, this will happen on a much slower, much more gentle time scale. But after about, according to my calculations, 10 to the 27 years, so that's a 1 with 27
27.
zeros after it. After that long, the Earth will spiral into the sun through gravitational radiation, and that's when the Earth will cease to exist because it will have merged with our sun, or
Right.
whatever's left of our sun.
Exactly. It'll just be a rock parked next to or embedded in another bit of a rock or what's left of it. Right. Again, very disappointing sort of future. You think, yeah, it'd be nice to sort of carry on, but obviously you can't beat the laws of physics.
Well, but if you want to say what are my bets, right? Like, okay, I was one of these last civilizations in Milkdromeda, and there's very little left that's going on now. I don't know what's going to happen, but it doesn't look good for this universe anymore. Is there somewhere else I can go? If you wanted to be really brave, you could get in a spaceship and say, you know what I'm going to try to do as my last gasp attempt to survive? I'm going to take my ship and I'm going to drive it into the black hole at the center of the galaxy, into this supermassive black hole. And the reason I tell you this is a last ditch effort is there are theories out there, they're speculative, but it's a possibility that when we take a spaceship into a black hole, that black hole could be a gateway into another universe. It may have fewer dimensions than this universe. It may destroy us or whatever goes into that black hole, but it's a chance. There's a chance that that's a gateway to another universe. So if you want to roll the dice and say, hey, I'm going to take a chance that there's something out there in this black hole that connects me to another universe, and I bet you this other universe is going to have more success than I do in mine with whatever's left, go for it. You
Yeah.
never know how it's going to turn out. I wouldn't bet on it, but it's better than the fate we believe we're headed for here.
Hopefully by then we might understand a bit more about black holes and be a bit better prepared for sort of sending yourself into one, because either way, well, you're going to have a slow death outside or an equally sort of drawn out one inside, really. So we've got now one from Cattle Sheets. How far out is the current model projecting the end of photons, of the era of photons?
So photons, these are particles of light. Any particle of light is a photon. In cosmology, what we talk about is what dominates the universe, what it has the most energy. The era of photons ended when the universe was about a few thousand years old, because as the universe expands, everything gets less dense. Radiation gets less dense, matter gets less dense. But radiation also, as we talked about, redshifted. As the universe expands, the wavelength gets stretched to greater and greater sizes, which means that they go to lower and lower energy. By the time the universe was only about 9,000 years old after the Big Bang, matter had already become dominant in terms of energy over radiation. So what we have today is actually a universe dominated by dark energy. Now, there are still photons, and those are always going to exist. The big thing is, when are you going to stop seeing them? When will the density of photons get so low that you would have to wait like a billion years just to have one of them hit your eye? And the answer to that is once that last black hole in the galaxy evaporates, that's pretty much it. Once those last photons from that black hole evaporation pass you by, you can pretty much count that for all practical purposes, you're never going to have another one hit. So I'll say the last photon you can reasonably expect to see happens when the universe is about 10 to the 100 years old, roughly a Google years old.
That's a long time. Not that we're going to be worried about that ourselves. Not right, let's see. Richard Collins. Where is the centre of the universe? If it's expanding out in all directions, does it have a centre? Has it expanded out from somewhere? Or is it just all going everywhere?
This is a really common question that we get, right? Because when you think of something expanding, you think of a center to it. You think of like, okay, if I took a balloon and I blew up the balloon, then I can point to the center of the balloon and say, there it is. I don't want you to think of the universe, though, as a balloon. I'd rather you think of it as a enormous ball of dough, of bread dough, with raisins all throughout it. These raisins are the galaxies. So when you bake your bread, what happens? You see the individual raisins, the individual galaxies, as the bread rises, they expand away from each other. You can put yourself on any raisin in that bread and say, I'm the center. I don't know how big this loaf of dough is. I can imagine it as big as I want, bigger than the whole universe, bigger than 1,000,000,000 times the universe. But wherever I am, whatever raisin I happen to be, wherever I look, I'm going to see the nearby raisins expanding from me slowly. The raisins that are more distant, I'm going to see them expand away more quickly as the dough expands more quickly. In the universe, the raisins are like galaxies, and the dough is like space-time. It is completely invisible, though. You can only see the galaxies. We don't even know if the dough is a physically real thing or if it's just a mathematical thing that we write down. So if you ask, where is the center of the universe? The answer is anyone, anywhere, will have equal claim to conclude it's me. It's right where I am, because that's the definition of what you can see. You can only see the light that's reached you in the 13.8 billion years since the Big Bang. So we would conclude that we're at the center, but someone 46 billion light years away would conclude they're at the center, and we would be right at the limit of what they could see. Someone outside of our observable universe would conclude they are the center. One of the things that people like to do is they like to say, okay, well, where did the Big Bang occur, and isn't that the center? Well, the answer is the Big Bang occurred, as far as we can tell, everywhere at once. So you can claim you're the center of the universe, but be aware that anyone, anywhere asking that question has equal right to make the same exact claim. It's better to say the center of the universe is everywhere and nowhere all at once, that every point has equal claim to claiming itself as the center.
Right, so I can't claim to be the centre of the universe, but then equally you could as well.
That's absolutely right. That's absolutely right. So I guess that just depends on how egocentric you are. If you're higher on egocentrism, maybe Boris Johnson level, you'll say, I'm the center of the universe.
Great. Okay. Lewis Bagnall. How do black holes not violate the information paradox? If they do, what implications would it have? And what is the information paradox? Please explain.
Let's start with that. Let's start with what the information paradox is. So we say information is good if it's conserved, right? I can take a book and I can set this book on fire and I can burn it and I'll say, aha, I've destroyed all the information. And you'll say, no, you haven't. If I was sophisticated enough and I tracked every molecule that was in that book to arbitrary precision and I gathered up all the smoke and I knew about every single particle, what it was doing, I could reconstruct all the information in that book. And you'd be right. If you did that, you absolutely could. If you throw something into a black hole, you'll say, okay, surely people don't know if I threw in a gas of hot atoms, or if I threw in a human being, or if I threw in a copy of the Count of Monte Cristo. You wouldn't know. All you can know about a black hole is its mass and its charge and how fast it's spinning, and that's it. Well, quantum information theory tells us that anything you throw into a black hole has a certain number of bits of information. And the way entropy works for black holes, and this is something that John Wheeler, the physicist from Princeton, discovered, is that the amount of information you can encode in a black hole is proportional to the surface area of the event horizon. So if you have something that falls into a black hole, in principle, that information is encoded on the event horizon of the black hole. So that's not a paradox. That's something that we believe we understand where the information goes. The paradox comes in when you bring up Hawking radiation and say this black hole is going to decay over time. It's going to emit radiation, and this radiation should just be black body thermal radiation. It shouldn't care how you made the black hole, what books went into it, what human beings went into it, what the temperature of a gas was that went into it. That is not a property that gets associated with the outgoing Hawking radiation. So when people look for resolutions to the black hole information paradox, and I say look for because I want to be very clear that even though Stephen Hawking has said multiple times the black hole information paradox is solved, it is not solved. This is still an open question that people debate, argue about, write papers on, and study. The leading theory is that somehow the information that's on the surface of the event horizon will get encoded in the outgoing radiation. So that's how we think information shouldn't be destroyed as a black hole evaporates, and that's how we think the universe should get around the black hole information paradox, but we aren't sure at this current point in time.
Okay then. Right. W. Weyer, is there a limit to the range of gravity?
You know, this is fun because gravity is an infinite range force, but it isn't infinitely fast. Gravity, just like light, is limited by a fundamental speed. They're the same speed. The speed of gravity equals the speed of light. So if you say, okay, I want to know 46 billion light years away at the edge of the observable universe, do I feel the gravity from what's out there? And the answer is yes, absolutely. But if I go 47 billion light years away, we haven't felt the gravity from what's out there yet, and they haven't felt the gravity from us. They will someday in the future because things are still coming inside the light cone. We can see more and more of the universe as time goes on. But there's a limit to how far away things can ever be that we'll be able to see it. And what's remarkable is I told you these galaxies are all unreachable if we left today at the speed of light. Any gravitational changes that happen to one of these unreachable galaxies, we'll never detect it. And anything that we do to change the gravity we emit, they'll never detect it. So, yes, gravity is fundamentally limited, not in range, but in terms of what range it can reach in a given amount of time. And that's because the speed of gravity isn't infinite. It's only the same as the speed of light.
Right, okay. Dan Haleberg, would the temperature of space drop even further, or is it as cold as it's going to get? I suppose you're saying here, is it going to get, it goes to absolute zero. It can't go any lower than that because, as far as I know, that's when nothing happens.
Well, it can't. The thing is, right now, it's not at absolute zero. We still have this cosmic microwave background, this leftover glow from the Big Bang. It means that even in the deepest depths of intergalactic space, you still have about 400 photons per cubic centimeter in there. And these photons, even though they're low energy, they keep space at a significantly above absolute zero temperature. It's about 2.7 Kelvin. But as the universe continues to expand and expand and expand, the wavelength of this light stretches. The number density of photons per cubic centimeter dilutes. And so if I wait until the universe is 10 times the size that it is today, then I'll find that, you know what? Actually, the temperature isn't 2.7 Kelvin, it's 0.27 Kelvin. And there aren't 400 photons per cubic centimeter, there's zero point 0.4 photons per cubic centimeter. And as you go forward and forward and forward in time, and the universe continues to expand, the temperature drops, again, asymptoting to absolute zero, and the number density drops. The number of photons per unit volume will asymptote but never quite reach zero. So as you go further and further and further into the future, yes, you will arrive at a time and a place where the number density of photons is effectively zero, the temperature of the universe is effectively zero, but it's never going to be quite zero. You wait around long enough and eventually a photon will reach you.
Right. One thing that I just thought of was that even if the photons were to become so sparse that there were maybe a fraction of one in a square kilometre or wherever, at the quantum level, things still pop into and out of existence, or so we're led to believe. At these extremely low temperatures where nothing is happening, is quantum mechanics still working at that point?
Yeah, quantum mechanics works in even empty space. But I do want to be careful. This is I think a big misconception in physics. People talk about these particle-antiparticle pairs as though if you got in there with a close enough magnifying glass or something, you'd be able to see particles and antiparticles just popping in to existence and then annihilating each other and disappearing. This is not what's physically happening. This is a visualization tool. It is a calculational tool. It is not what's actually happening. If you went to empty space and you said, okay, I'm going to put my detector in here and I'm going to look for particles and antiparticles, you wouldn't find any. You don't find them popping in and out of existence. This is just a tool we use to calculate the 0 point energy of empty space. So there is empty space. It really is empty in terms of particles in there, but it isn't empty in terms of the fact that the energy in empty space is not zero.
Right. Well, now you're getting beyond a point that I can understand. So, um, I think we'll just go to wrap this up here, and we've got one final question from Michael Ketzin. Oh, yeah. Sorry if my pronunciation and foreign names, everybody knows it's not brilliant. Michael Ketzinzir is 74. Ethan, what is your personal opinion of how the universe will end?
Well, so I don't think the universe is going to end. I think everything in the universe will come to an end. But I think the universe will continue to slowly expand and exist for all eternity. We might have, like I told you, we might have the galaxies all merged together into these collapsed groups, and all these groups will accelerate away. And we might have everything in these groups, gravitationally eventually interact with each other and kick all the normal matter out of galaxies except for the black holes. And then the black holes will decay away. So all you'll be left with are these big diffuse halos of dark matter and these individual masses or mass systems just spread throughout intergalactic space. And the universe will be cold and empty. And that, I think, is fair when you reach that point of maximum entropy in the universe to say, this is the heat death of the universe, where time continues to pass and the laws of physics continue to exist, but nothing interesting happens. No work can be done. Nothing requiring energy is ever going to happen again. No particles will collide or interact. That's how I think the universe is going to end. We started with a bang, and I think the best evidence we have today says the universe will end with a whimper.
Sounds like daytime TV almost. Well, that seems to be about it. So we're going to go out. It starts with a bang and ends with a whimper. And on that note, I think that we're almost coming to the end of the show. I would like to thank Ethan. Now, Ethan, where can we find more out about yourself Well, you
Well, people wrote a Wikipedia page for me if you want to like online stalk me. But if you want to find out more about the universe and what I talk about and what I love to do, there are some great places to find me. You can follow me on Twitter. It starts with a bang. You can check out my first two books on Amazon or anywhere books are sold. One is Treknology, which talks about the real life science behind the technologies in Star Trek, and the other is Beyond the Galaxy, which is a fabulous introduction to astronomy and cosmology that's beautifully illustrated with no equations if you want to know what we know and how we know it about the universe. And finally, for those of you who are up for a very exciting trip, next January I will be leading an astro tour of Iceland, where we will be looking for aurorae, we will be watching the total lunar eclipse next January, and we will be just having a great time in the natural settings, hearing stories about the universe. If you want, we still have some spots open, and you can find out more at astrotours.co/starts with a bang.
Great. Well, that sounds really interesting, especially over in Iceland as well. That's quite an interesting place over there. I've never been, but from what I can gather, it seems like a very interesting place.
And in January, we get 16 hours of darkness almost as far north as the Arctic Circle. So there's really
Yes.
few better places in the world to go looking for the aurora borealis.
Yes, very good, very good. Okay then, so that seems to be just about it really. I'd just like to thank all our moderators for helping out with the questions, and also all the people who have asked questions and everybody who's been watching today. I'd like to thank all our Patreon supporters for their ongoing support, and you can obviously find out more about that with the link that will probably pop up somewhere later on there. I'd also like to just say thank you very much once more for Ethan for coming along and illuminating us on the end of the universe and what we might expect. Of course, we're not going to be around. We're going to be long gone by then, although we may have reincarnated a few billion times. You never know. We don't know what's going to happen. But anyway, thank you very much. And it just remains for me to say thanks for watching. Thumbs up. Don't forget to thumbs up, share, and subscribe. And I'll leave you with the end of the show. Thank you very much. Goodbye.